Welcome back to the channel. So today in this video lecture we'll be solving this problem, the Enchanted Forest. This problem has been taken from the Codeforces Div 2 round, and I solved this problem using binary search. Although binary search is an overkill for this problem, it's just an implementation problem, but just a thought process. I could observe those patterns which shows that this problem can be solved using binary search. So if you have followed the playlist till this point, then you would be able to figure out that yes, this problem can be solved using binary search. So let's read the problem statement. Marisa comes to pick mushrooms in the enchanted forest. So the enchanted forest is basically some kind of magical forest that we have, in which the mushrooms grow magically. Okay, and let's see, the enchanted forest can be represented by n points on the x-axis numbered from 1 to n. So the enchanted forest is basically a number line where we have n points. Each point is basically a location for growing the mushrooms or the magical mushrooms. So we have 1, 2, 3 and so on. These are the locations for the mushrooms, and each location basically grows mushrooms. Okay, so let's see how the mushrooms are grown. Before Marisa started, her friend Pacholi used magic to detect the initial number of mushrooms on each point. So initially we have counted the number of mushrooms magically somehow, which are represented by an array of n integers a. So this a array is something like a1, a2, which represents the number of mushrooms at each position, number of mushrooms on the first position, number of mushrooms on the second position, and so on. Marisa can start out at any point in the forest on minute 0. So initially when t is equals to 0, Marisa can start at any point out of these n points. Each minute the following happens in order. So these are the three activities which happens in order each minute. She moves from point x to y. So let's say Marisa stands on point x, then she moves to point x from x to y, such that the point is either adjacent to this x, it is either left point or right point, or it is the same point on which it stands. Let's say the new point is y, then x minus y must be less than equals to 1. Modulo x minus y must be less than equals to 1. Fine, possibly y is equals to x. It is also possible that the Marisa do not move at any of the adjacent points, but it just stands at the same point. Okay, the second activity is that she collects all the mushrooms on point y. So when she moves from point x to point y, she collects all the points from position y. And the third activity is a new mushroom appears on each point in the forest. And after this activity, after collecting this mushroom on y, a new mushroom appears on every position of the forest. So these are the three activities which occur in this order in every minute. She cannot collect mushrooms on t is equals to 0. So while she is starting, she may start from any position, and from that position she can't collect any mushroom. Okay, now what do we have to do in this problem? Marisa wants to know the maximum number of mushrooms she can pick after k minutes. So we have k minutes. Marisa is in the forest for k minutes, and we want to find the maximum number of mushrooms that she can pick from this forest. Again, we have to maximize something. We have to maximize the number of mushrooms. Let's say x. X represents the number of mushrooms, and I want to maximize this number such that we have k minutes and we can perform these activities in this order, each of these k minutes. So that's all. We just have to simulate the process. We just have to simulate these activities. And since I want to maximize this x, this observation points to the application of binary search algorithm. This is where binary search clicked to me. Okay, now we would have an array of maximum length 10 raised to the power 5, and the number of minutes that we may have may go up to 10 raised to the power 9, and the maximum number of mushrooms at any position of this forest may go up to 10 raised to the power 9. Okay, and the sum of n over r test cases does not exceed 2 into 10. Okay, so let's better understand this problem statement using an example. Okay, so let's take this example. We have 5 positions where the mushrooms are magically appearing. We have 2 minutes of time, and these are the initial mushrooms that we have on these 5 locations. Okay, now Marisa starts from very first position, let's say from this position. So the positions are numbered from 1 to 5. 1, 2, 3, 4 and 5. She starts from the first position, and in the one move let's perform the activities given in the array. So at t is equals to 0, Marisa is standing on the first position. In the very first minute she moves to the adjacent position, that is position number 2, and 2 minus 1 is less than equals to 1, that is true, and she collects all the mushrooms which are present on the second position or new position, which are 6. Then the third activity was that on every position 1 extra mushrooms appears magically. So we have picked all the mushrooms from the second position. After picking up the mushrooms from the second position, the number of mushrooms at every position would be 6, 1, 2, 3 and 4. Okay, now 1 minute has elapsed. We have elapsed 1 minute. Now in the second minute, Alisa moves to the first position. She moves to the first position. We have two options. We can either move here or we can move here. So let's say we move to the left side because we have more number of mushrooms on that side. So we move to the left side, and we pick all the mushrooms which are there. We have 6 mushrooms over there, and after that minute has elapsed, we would have 1 extra mushroom appearing on every position. So the final array would be like 1, 2, 3, 4, 5, and these will be the number of mushrooms that we would be collecting, that is 12. Okay, so now you can try to start from every position out of these 5 positions and perform the activities in the order in which I performed them, that is move to the adjacent position y, pick up all the mushrooms, and then grow 1 more mushroom on every position. Okay, and you will never get an answer greater than 12. So maximum answer is 12 for this test case, and 12 is the output for this test case. So how would I solve this problem? What is the strategy to solve this problem? Let's see that. Now the intuition to solve this problem is simple. Let's say x represents the number of mushrooms or the maximum number of mushrooms which I can collect, and that's the target answer. I just want to maximize the number of mushrooms. So again, since I want to maximize the variable, maximize the answer, this is a binary search problem, or rather binary search over the answer. For that we must have a range for this answer. Now since x is the answer, we can collect x mushrooms. We can always collect x minus 1 mushrooms. We can always collect x minus 2 mushrooms, and so on. We can always collect 0 mushrooms. So this is the extreme case when k is like something like 1, and so we can say, let's say low is basically 1. So this is 1 rather than 0, because let's take this test case when we have only 1 position in the enchanted forest, we have only 1 minute, and that's all in this, and the number of mushrooms which are present on that position are also 1. So we just stay on that position from x to x. Let's say x is the initial position, that is 1, and then we pick the mushrooms on that position, and we pick 1 mushroom, and we grow 1 more mushroom over that position, so we would have 1 mushroom at the end, and that is the lower limit, 1. Now if I can collect at max x mushrooms given k minutes in some k minutes, then I will never be able to collect x plus 1 mushrooms, because this is the upper limit. I won't be able to collect x plus 1 mushrooms in k minutes, because that's the maximum I can get. Similarly, I won't be able to collect x plus 2 mushrooms, and so on till 10 raised to the power. So what would be the right extreme? What would be the right extreme? The maximum number of mushrooms that I can collect goes up to 10 raised to the power 9, while the maximum time that we can utilize to collect the mushrooms also goes up to 10 raised to the power 9. Okay. Now, to handle these type of constraints, we may have very large answer, an answer of, let's say, comparable to 10 raised to the power 18. So to handle these kind of extreme cases, we take a very large number, that is 10 raised to the power 18. Okay, so that's all. Now, so the target is to find this x. We have the search space from 0 to 10 raised to the power 18, and we want to find this x now, which is just the last row, because this portion represents the good mushrooms, while this portion represents the bad number of mushrooms. It's not, it's count, bad count. Why? Because we can't collect these much mushrooms. We can always collect these much mushroom, these number of mushrooms. Okay, so these are good, these are bad. So it's similar to finding the last true element, which we discussed in the very first video of the playlist. Fine, so we perform the binary search over this range from 0 to 10 raised to the power 18. We find the mid element. We would check if this mid lies on the good side or it lies on the bad side. If it lies on the good side, let's say here, mid lies here, then that means the answer, which is this x, lies on the right hand side. So the search space in that case will be reduced to mid plus 1 to high, while this mid, which I have guessed here, can also be the potential answer, because maybe we end up on this integer. The mid is on this integer x. Okay, so that's how we reduce the search space in this case, while on the second case we land on the bad integer, we land on the bad number of mushrooms. So that means, let's say mid is here, the answer lies on left side over here. So the search space will be reduced to low to mid minus 1. Fine, so eventually we will arrive at our target x while performing these iterations, while reducing the search space till one single element is left till one single element is left. That's what that while loop in the binary search represents. Okay, so that's all we have to do in this problem. Now, since we have identified that this is a binary search problem, we know that if you have followed the series, the main logic or the main implementation is basically getting that predicate function, getting the definition for the predicate function. That is, let's say, that is how to check if the particular mid that we have guessed lies on the good side or it lies on the bad side. Fine. So how would I check that? That's the main challenge. So let's observe few things which will help us to find that that mid, that validity. Okay, so let's say we guessed a mid. We can divide it into two separate cases. The first case is that when n is greater than equals to k, this is case number 1. The number of minutes that we have are less than the number of elements that we have. This is the case when we won't be able to traverse every single position in the forest. That's the case number 1. Case number 2 would be when we would be able to traverse every single position in the forest, maybe multiple times. That's case number 2. We would see that the implementation for these two cases is entirely different. Okay, in at least in my solution, I separated these two test cases. Okay, so let's discuss the very first test case, that is when we can't traverse every single point, every single magical point in the forest. Like this one, k is less than equals to n. This is case number 1. Let's say we start from the very first position. We start from this position. And in the very first move, k is 2 here. We can move to the adjacent number, that is 6, collect those mushrooms. So we collect 6. Then on the second minute, I go to the previous mushroom, that is to the previous location, that is position number 1. And after 1 minute, I know that the mushrooms would be like this: 6, 1, 2, because one extra mushroom would be grown at every position of the forest. So I collect these 6 mushrooms from the position number 1. So 6 plus 6 would give me 12. That means if I start from the very first position and start collecting the mushrooms, then I would be able to collect 12 mushrooms from the first 2 consecutive positions. That is case number 1. Okay. Now there can be another case. Maybe from this position 6, we could move to the third position. Who knows? Who knows, we have better number of mushrooms on this position. This is another case. We moved here back to position number 1, but there was also an option to move to the next position. Maybe we get a better answer there. So to handle that, what I am doing is, since this is 6 plus 6, 12, I'm traversing every k consecutive positions. So I traversed the very first k consecutive positions. I collected the mushrooms from there. Then I traverse the next k consecutive positions. I pick up the mushrooms from those k consecutive positions. Then I pick mushrooms from the next k consecutive positions. Then I pick mushrooms from the next k consecutive positions. And I take maximum of all the mushrooms collected. Okay. So let's take this second case when I start from the second position, and from this second position I move to the third position, that is this one, and I pick the number of mushrooms from the third position, 1. Then I move back to the second position and I pick the mushrooms from there. One mushroom would have been grown in 1 minute, so that's why I'm picking up 7. Okay, and that is going to give me 8. So what I'm saying here, if I start from the second position, then I can get 8 number of mushrooms if I traverse consecutive k positions starting from 2. Let's start from the third position and traverse these 2 positions, 3 and 4. In that case, move from 3 to 4, pick up 2 mushrooms, move back to 3, pick up 2 mushrooms, because 1 mushroom is extra added, giving me 4 mushrooms. Start from 4th position, move to 5th position, pick up these 3 mushrooms, move back to 4th position, pick up 3 mushrooms, giving me 6 mushrooms. So out of all these mushrooms, the maximum mushrooms collected was here. So the answer would be 12. That's the strategy which I used to handle this case. Okay, fine. Now observe here, how would I calculate that? Let's, so this is nothing but what I am doing here. Since we have k positions. I have to traverse k positions starting from the first position, and it is nothing but 6. 6 is the number of mushrooms on the second position on which I am moving. Then we had 5 mushrooms on the position where we left, plus how many mushrooms would have been added? How many mushrooms we have to add to compensate for the extra mushrooms which are grown? Let's say k is 3. Let's say k is 3. Let's take this array again, 5, 6, 1, 2, 3. Or let's say k is 4 rather. So we start from this position, that is first one, move to second position, pick up 6 mushrooms, move to the next position here, that is third one, and pick up 2 mushrooms, plus move to the fourth position, that is this one, and pick up 4 mushrooms. Why? Because in the very first minute we would have 2 mushrooms here, we would have, and on the second minute we would have 4 mushrooms here. Okay, then I have 1 more minute. And in that minute I would be collecting the mushrooms from the this position, that is from this one, and we would have 3 plus 3, that is 6 mushrooms. So after k minutes we basically adding k mushrooms at every position. So we started from the very first position, that is this one, we picked up all the mushrooms from these positions, that is 6 plus 1 plus 2 plus 3, but we also added mushrooms which are grown over that span of time. So 1 extra mushroom on the second position here, 2 extra mushrooms on the third position. Why? Because okay, so 1 extra mushroom on the third position, 2 extra mushroom on the fourth position, because 2 minutes will be elapsed, and 3 extra mushrooms on the fifth position, because 3 minutes would have been elapsed. That is going to give me 1 plus 2 plus 3, that is 6 extra mushrooms which I had to add in this sum. 6 plus 1 plus 2, 6 plus 1 plus 2 plus 3, and let's say we have k minutes. K was 4 here, so if k is 4 I had to add 6 mushrooms, because k was 4 I had to add mushrooms which are grown in k minus 1 minutes, k minus 1 minutes. So how many mushrooms would I have been adding? Since after every minute 1 mushroom is extra added over every position, after 2 minutes I would have 2 extra mushrooms over those positions, and on the 1 minute I collect 1 mushroom, on the second minute I collect 2 mushrooms, on the third I collect 3 mushrooms, and so on till k minus 1 minute, and the sum is nothing but k minus 1 multiplied by k divided by 2. So these are the extra number of mushrooms which I have to add apart from the usual sum that I am calculating. Fine, I hope you got the idea how I am deriving this formula. So let's sum up all these ideas on the next slide. So I was handling case number 1 when k is less than equals to n. Okay, this is case number 1. Now, or more precisely, let's call it k is less than n. Let's handle the other case on the, let's handle the this condition equal to on the second case. Now for this case we know the sum that I want to calculate is nothing but, the sum is basically we start from some position I and we keep on summing these numbers ai plus 1 plus ai plus 2 and so on till a I plus k minus 1. Okay, so because we want to sum for k positions, I want to sum for k positions. So let's say if k is 2, k is 2, then I would sum from I is equals to 1 till, okay, so this is the sum which I want to calculate, where I is the starting position. These are the k integers we have. Now, this is basically the window sum. This is basically the window sum, the sum of the current window of k elements, which is starting from the index I, and the starting index is basically goes from I is equals to 1 till n minus k plus 1. So this is the starting index, and for every window I want the maximum of all the sums, maximum of all these sums. That's what I want, where for every window I have to add the number of extra mushrooms which are added, which are grown over those k positions for which I am collecting the mushrooms. For that I have to add k multiplied by k minus 1 divided by 2. That's all. This is how I'm gonna handle the case number 1. I will take a maximum of these numbers, maximum of these window sums, and in that sum I'm gonna add this number. So let's call it max mushrooms. Let's call it max mushrooms, max mush, which is this. Now from that boolean function, if I encounter this case, then I will calculate this sum, this maximum sum, and at the end I will check if this max mush is, we have to check if this maximum sum achieved is greater than equals to mid. This indicates that this sum, which indicates that this mid lies on the good side, mid lies on the good side. Okay, because I can achieve this mid as a sum. So that's how I would handle case number 1. Let's discuss the case number 2. When the number of minutes which we are given are greater than or equal to the number of elements or the number of positions where the mushrooms appear magically. So how would I handle this case? Let's see that. Okay, so this is the scenario. We are given 5 elements in the array. We are given 7 minutes. This is the time that we have, and these are the elements which are there in the. After picking up these mushrooms, that would take 2 minutes. Here I would have 2 mushrooms. Here I would have 1 mushroom. Here I would have 3 mushrooms, 9 mushrooms, and 8 mushrooms. And I'm standing over here. Okay, and I'm standing over here. Okay, so let's handle this case, that is when k is greater than equals to n. How do we solve for this case? Let's see that. Now, one of the very naive thought process can be just start from the very first position and start picking up all the mushrooms from left to right, then traverse back, then traverse from left to right, and so on. That is traversing back and forth and picking up all the mushrooms. This is one of the most naive thought process which may come into the mind. Let's see the problems with this approach. Okay, so let's say we have, since we have k moves, if we follow this strategy, that is move back and forth, then let's say after n minus 1 moves, I would be standing at this position. I would be standing at this position. Okay, and after this n minus 1 moves, the number of mushrooms that I would have at these positions would be like n here, n minus 1 here, n minus, let's say, 2 here, and so on till this last position, anything like on which I'm standing. It would be like 1 after we collect the mushrooms from that position. Now the mushrooms are n at this point, but I won't be able to collect these mushrooms. If the remaining moves, let's say the remaining moves are n divided by 2 or something less than n, such that we can't reach this position. In that case, after performing these many number of moves, I would have n plus n by 2 mushrooms here, n plus n plus n minus 1 plus n by 2 minus 1 mushrooms here, and so on. And we will never be able to pick up these mushrooms. It is not possible to pick them up. Okay, so that's not an optimal strategy to pick up the mushrooms like this. Okay, so moving back and forth, starting from the leftmost position, moving to rightmost, then coming back to the left, is not an optimal way to solve this problem, to solve this case. So how can we solve that when k is greater than n? The optimal way to do so is just keep sitting at the very first position till the number of moves remaining are n minus 1. Why? Because when the number of moves remaining are n minus 1, then the extra residue or elements or the mushrooms which will be added at this position would be n. At this position it would be n minus 1. At this position it would be n minus 2, and so on. At this position it would be 1. Fine. Till then, keep sitting at this position and keep eating the mushrooms which are growing at this position. Okay, that's the optimal strategy to solve this problem, to solve this test case. Okay, so what is the answer? The answer is simple. We have k moves to make. Okay, we have k moves to. So now when I have these n minus 1 moves, and this is the configuration, I start moving from this position towards the last position, and I start eating these mushrooms. So I eat these mushrooms. I eat first mushroom on the first position, then I eat 2 mushrooms on the second position, and so on. Then I eat n minus 2 mushrooms on this position, on the third last position, n minus 1 mushrooms on the second last position, and finally n mushrooms on the last position. So when I reach this position, the last position, mushrooms which will be on the first position would be n. The mushrooms on the second position would be n minus 1. The mushrooms on the third position would be n minus 2, and so on. So these are the mushrooms. So these are the mushrooms which I will never be able to eat. Okay. Okay, so let's think about the very optimal case when I would be able to eat the maximum number of mushrooms while I can make k moves. Okay, now observe that let's say we keep sitting at this position, since I want when I so what I want is when I arrive at this position, at the last position, I I can eat maximum mushrooms. The maximum mushrooms which can be added to this position are n. So let's say I keep sitting at this mushroom, this position, and keep eating the mushrooms which are appearing there till n minus moves are remaining. So how many? 4 moves are remaining. We have 7 total moves. We have 4 moves remaining. So for the first 3 moves, I keep sitting at this position. So on the very first move, I eat 5 mushrooms from there. Then on the second move, 1 mushroom would be added. So 1 mushroom would appear and that I will eat that mushroom. And 2 seconds has been elapsed. Now on the third minute, 1 more mushroom would be there and I would eat that mushroom. That is going to give me 7 mushrooms. So I would have eaten 7 mushrooms before I move to the second position. And I have made 3 moves while sitting at the very first position. And I have exactly 4 more moves to make. So on the first move, so on the fourth move, I move to this adjacent cell. I move to this adjacent move. Since 2 minutes has already been elapsed here, on the third minute I would be able to pick up these mushrooms. 2 more mushrooms would have been there. 3 more mushrooms would have been on the third position when I pick up this mushroom. 4 mushrooms here, 5 mushrooms here. Okay, so let's think of the ideal condition. The ideal condition is that the extra mushrooms which appear at each position would be k after exactly k moves. So k here, k here, k here, k here, and k here. That is going to give me n multiplied by k. These are the extra number of mushrooms which will be added at each position. Now, but since I'm picking up the mushrooms while I am moving from left to right, how many mushrooms I won't be able to eat out of these n multiplied by k moves. When I move from here to here, I would leave 1 mushroom there. When I move from second to third, I would leave 2 mushroom there. When I move from 3 to 4, I would leave 3 mushroom there, and so on till n mushrooms. That means I won't be able to eat n multiplied by n plus 1 divided by 2 mushrooms. Okay, so let's think of it like this. We have k mushrooms. Let's say in k moves we would grow k mushrooms at every position. Okay, but since I'm moving from left to right, I won't be able to add these many mushrooms for each position. So I have to subtract these many mushrooms from these total n multiplied by k mushrooms. Okay, so the number of mushrooms finally would be the sum of the mushrooms which are present initially, that is 5 plus 6 plus 1 plus 2 plus 3, plus this total number of mushrooms which I can have after k moves. But since I am moving from left to right, I won't be able to eat these many mushrooms, n multiplied by n plus 1 divided by 2. So that is going to give me, so the sum would be, the equation for this test case would be sum of all elements in the array where I goes from 1 to n plus the total mushrooms which I can add after k moves minus the number of mushrooms which I won't be able to eat. Okay, so that is the equation for this test case. This is one of the ways to think about this case. There are other ways which can be used to think about this particular case. Now this is not the way which I thought during the contest. My thought process was extremely difficult and it is hard to explain here. So that's why I explained this approach to solve this case as well. This is the easiest approach which I found, and That's all for this problem, and I would be attaching the code for this solution in the description below, so make sure to check it out. And let's implement the solution. Let's see the implementation of this solution in the next slide. This is the implementation of this max mushrooms function. Takes in the number of mushrooms, the number of moves, and the array that we have. Answer, initialize answer to 0. We take a low variable, initialize it to 0. High variable, initialize it to a very large number. And then I run the usual binary search to find the last true element. Find the middle element, check if it is valid, if it lies on the good side or it lies on the bad side. Reinitialize the range. Since it lies on the good side, the range will be reinitialized to mid to high, and this mid can be the potential answer. Otherwise, the range will be initialized to low to mid minus 1, because the answer lies on the left side. And finally, this low will store the answer. This is just the implementation of the last true function which we discussed in the first video. Now let's see the definition of this check function. So this is a check function where I calculate the size of this array. This is the very first case which I am handling. I initialize a variable result that is going to store the maximum number of mushrooms which I can eat, and then I compute the sum of all the mushrooms that I have in the array, and this I initialize to the current sum. Okay. Now here what I'm doing here, this is the sum for the very first window. So this is not n, I'm not iterating over the entire array, I'm iterating over the very first k elements. So I'm summing up the window, I'm summing up the element in the very first window of size k. Then I will simply compute the same sum for the next windows, obviously starting from the kth element till the last element. That's what I am doing here. This is nothing but adding the difference between the I minus kth element and the kth element. That's what I'm doing here. Why? Because while shifting from, let's say, 1 2 3, I want to shift from 1 2 to 2 3. I already have the sum of 1 plus 2, that is 3. I want to get the sum of this 2 and 3, and I'm standing on this position, that is position number 3 on this integer. All I have to do is to add the difference between 3 and 1. That would be 3 minus 1, that is 2. So if I add 2 here, I will get the sum of this window. That's what I'm doing here. And I will simply find the maximum of all these sums, all the sums of these windows. And finally, after I get the maximum sum, since I'm traversing over k elements in a series, these many mushrooms will be appearing on those k positions, on those k minus 1 positions. So let's say we have 1 2 3 4 positions. I move from here to here, then from here to here, then from here to here. One mushroom will be added in the very first second from here. Two mushrooms will be added here. 3 mushrooms will be added here. That means for 4 positions, I would have k minus 1, 4 multiplied by 3 divided by 2 extra mushrooms, because 1 plus 2 plus 3 is nothing but it gives me the sum for, because 1 plus 2 plus 3 is same as writing as 1 plus 2 plus 3 plus and so on for k minus 1 positions, and the sum for that is nothing but k minus 1 multiplied by k divided by 2, which I am adding here. And finally I will check if this result lies on the good side or it lies on the bad side. If it is greater than equals to mid, that means yes, it lies on the good side, and I will return true from here. Otherwise I'll return false from here. So let's handle the second case. The second case is that when k is greater than n. In that case, add up all the elements in the array. Now for k moves, while I move from left to right, I would have n mushrooms at the end. I would have n mushrooms, n minus 1 mushrooms here, n minus 2 mushrooms here, and so on, which would not which I would not be able to eat. While the sum of these mushrooms is nothing but n multiplied by n plus 1 divided by 2. So I would eat all of the mushrooms which were already there in the array. I would eat n multiplied by k mushrooms, because in the like this is I'm considering, because I can have, for k moves I can have n multiplied by k mushrooms which are extra added to it. But since I'm moving from this position to the last position, when I would have n minus 1 moves left, these are the number of mushrooms which I won't be able to eat out of these n multiplied by k mushrooms. This is the extreme case which I'm considering, the total number of mushrooms. And that's why I'm subtracting this n into n minus n plus 1 from this sum. And while at the end, I will check if the sum is greater than or equals to mid. That means it lies on the good side or it lies on the bad side. So this is one of the ways to think about this case. And there are other ways which are more complicated. This is the easiest way which I found. So you can try to think of this second case in other ways by yourself. And but that's all for this problem. Let's implement this solution in code. But before that, let's discuss the time complexity. We can see that this is just the binary search, so the time complexity for this would be nothing but log of 10 raised to the power 18. While for this predicate function, I can see that I'm traversing over the array at most once. That is going to give me n time complexity. So it is nothing but n multiplied by log of this factor, which is a constant factor. While the space complexity is constant, because I'm not using any extra space. Okay, so that's the solution for this problem. uh, Binary search is basically an overkill. We don't even need this binary search to solve this problem. We can solve this problem without using binary search, but since we had this pattern, we had to maximize something, maximize the number of mushrooms. I could think about binary search and it worked for me. Although there are other solutions which don't even require binary search, this is just an overkill. Fine, so let's implement the solution in code. Okay, so this is my solution class. Create a function which represents the maximize mushrooms, which takes in this vector v, let's call it v, and the number of moves that I have. So I calculate, so this is, let's take it long, let's say this is long because the answer can be very big. So instead of using an int variable, I would be using long, the number of okay, and let's define the boundaries. Long, low boundary to 1, high boundary to 10 raised to the power 18, so 1 18, and run the usual binary search. Low is less than high, find the middle element, so if this is a valid, this lies on the good side, then that means the reduce the search space to this one, otherwise reduce the search space to second half, otherwise reduce the search space to first half, and return this low, which will store the answer. So this is similar to implementing the last true. Now let's create this check boolean function which takes in this vector. So it's not only mid, we're passing in the vector v, we're passing in the mid, we're passing in the moves that we have. So take the vector v, the number of moves that I have. We don't have to pass k. Do we have to pass k moves? Yes. So we pass k moves, then I pass this mid. And let's handle the very first condition, that is k is greater than n, k is less than n. So in that case, let's call it res. So long result initial. We will first find the sum of the very first window of size k. Start from the first element, iterate over the k elements, and add all of the k elements first into a variable. Then initialize another variable current sum to this result so that we can find the maximum sum in any of the windows. So iterate over all of the windows starting from the second window. Okay, and all we have to do is to add the sum of the ith element, difference of the ith element from the from this element. Then I will simply and at the end I will have to add these many number of mushrooms which will be grown at these k positions, and at the end return if this result that I have got is greater than equals to mid. If it is, then this mid lies on the good side, otherwise it lies on the bad side. Then otherwise let's handle the second case when k is greater than n. So initialize a variable sum to 0. Find the sum of all the elements which are present in the array. Sum all the elements. Now also add the extreme case. For k moves, the total number of mushrooms that I can grow would be n multiplied by k, while I won't be able to collect n multiplied by n plus 1 divided by 2 mushrooms. And at the end also check if this lies on the good side or on the bad side. Sum is greater than equals to mid or not. Finally, this is how this check function will be implemented, and that's the implementation of this solution in C++. Let's see the implementation in other languages. Okay, so this is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and continue in the binary search playlist till end. Will be few more problems, and then we'll be wrapping up this series, and I hope to see you all in my next video.